Hello again. This is video lecture 29.1, and we're starting chapter 29, which is all about calculating the magnetic field that is created by electric current. Okay, so the big picture for this whole chapter is quite simple to state. Electric current, moving electric charge, produces magnetic field. Just like any electric charge, moving or not, creates electric field, moving electric charge, what we call electric current, creates magnetic field. This was discovered quite by accident historically, when a physics teacher in the 1800s discovered that when you set up current in a long wire and then held a compass, right, a magnetized piece of iron near it, the needle would be deflected. That's how we learned that electric current produces magnetic field. So our task for this chapter is, given that reality, once we're given a steady current, steady means not changing with time, or, to be perfectly honest, if it is changing with time, not too rapidly. So we'll just call it a steady current. We want to calculate, at any location in space, the magnetic field B that is created by that current. And when we did electrostatics, we spent 2 whole chapters studying the electric version of that scenario. Given a configuration of electric charge, calculate at any location in space the electric field created by that charge. Now we're doing the magnetic version. Given a steady electric current, pick a point in space and calculate the magnetic field created by that current. So let's dive right into section 1, chapter 29, which is going to give us the necessary physics to calculate the magnetic field due to a current. And it is an experimental result. Okay, named after some individuals, and they are who they are, and they did some of the experiments, and so they get it named after them. And their last names are Biot and Savart. And as we discussed this result in the United States, we pronounce those names Biot and Savart. So it's often called the Biot-Savart law, but it is really just a statement of an experimental result, which we are now going to state in more modern language, and it's going to enable us to calculate the magnetic field produced by a steady current. So the picture over on the right is meant to represent what is labeled there, a current distribution. And of course, what it's meant to show you is a portion of conducting wire. And you can see it's got some pretty complicated shape. It's winding around in the plane of the screen. And of course, it's not just sitting there completely isolated from anything else, as the drawing seems to imply. Of course, it's connected to other things down here and up here. But we're just meant to see this portion of the wire. And somebody has created conventional current I, which is flowing roughly upward in the plane of the screen. And then we've picked a point over here on the right, somewhat arbitrarily chosen. It's labeled P. And our task is to calculate the magnetic field produced at point P by this current distribution in this wire. And the experimental result says that you have to immediately jump into calculus. That is to say, you have to imagine breaking up the wire into a whole bunch of little tiny pieces, okay? Each of length ds. And you have to calculate the magnetic field contribution, dB, at point P from that little piece ds. And so what they've done is they have highlighted a little piece there in red. It's a little infinitesimal length of the conducting wire, ds. Right? It's that part highlighted in red that you can see. And the formula, this experimental result that we're about to state, will enable us to calculate dB, the magnetic field contribution, tiny though it is, from this little length of the current carrying wire, ds. Now, in order to apply this result correctly, we have to be clear on a number of different vectors that we'll have to deal with. After all, magnetic field is a vector quantity. And so here's what they've done in this picture. They have kind of shown the tangent line to the wire at the place where the little ds is. That's this dashed line right there. And they have created a vector ds, which is this blue arrow right there. And it is two things. One, tangent to the wire at this location, and in the direction of the current at this location. And so that's why the ds arrow, drawn in blue, is pointing the way it does. It's tangent to the wire at this location and in the direction of the current. Okay? ds arrow. All right, now here's another important thing. Just the straight line distance from the little piece of wire ds to the point P. That distance is labeled little r. And that's all it is, the straight line distance from the little element ds to the point P. Now here comes another vector, and it's drawn in red with its tail at the little element. And it points directly towards the point P. And that is r hat. You could call it a radial unit vector, but the hat means it's a unit vector. So it's dimensionless, it has no units, and its job is merely to point from the current element, ds, towards point P. Notice then that there is an angle that they have labeled theta between the two vectors ds and r hat. That's important too. All right, now with all those vectors in mind, we are now going to state this experimental result for calculating the magnetic field contribution at point P from this one little tiny element of wire. So the contribution will be labeled dB arrow, and it will depend on the current I, that's right there, and then it's going to have some constants out front. Now remember when we calculated the electric field from a point charge, call it dq, it involved dq over 4 pi epsilon 0. Remember that old friend? Epsilon 0 is just a constant. Its value depends upon the choice of units we're using, SI, and it's called the permittivity constant, epsilon 0. There's a similar constant that shows up when you calculate magnetic fields, and the symbol for it is mu sub 0. And it's, in this case, upstairs. And then there's still a 4 pi downstairs, like we had in the electric case. But note then, the constant is different now. It's mu 0, not epsilon 0, and it's upstairs, not downstairs. But it is a constant, and it just has a numerical value, depending upon the system of units. And it has a name. So we might as well state the value in the name. This constant mu 0 has the value of 4 times pi times 10 to the minus 7. The units are Tesla times meter per ampere. And it is called the permeability constant. And it's going to show up now for the next several chapters. And it is the constant that appears in the magnetic field law, okay, for dB. Mu 0. It's upstairs. We know its value. We know its units. And we know its name. Now we're just going to have to carry it around, as it were. Now what else is there in this expression for the magnetic field contribution? Well, in the numerator, I have to have something that gives me a vector direction, right? The direction is coming from a cross product. Not surprising given what we learned in chapter 28 about magnetic forces. They all involved ultimately a cross product. And the magnetic field law involves a cross product. And it is the cross product of, of the two vectors I spent so much time talking about in the figure. And that's why I did spend time talking about them. They show up in the magnetic field law. And it is the cross product ds cross r hat. And that's the order. ds first, cross r hat second, then divided by the distance r squared. So yes, it is an inverse square law, just like the electric field law. Okay? But the numerator looks a bit different. It's got a mu0 constant upstairs, it's got the current I upstairs, and then it's got that cross product, ds cross r hat. Now let me just point out another way you'll see this result written. And it's based on the fact, I'll write this over here to the right, that the unit vector r hat can be expressed as a vector r arrow over the magnitude of r arrow. Now the vector r arrow, let me get rid of some of my writing here, would point from the element ds all the way to the point P. And that would be r arrow. So to get r hat, which is the unit vector, you take r arrow divided by the magnitude of r arrow. In a lot of ways, the books will write the magnitude of r arrow is just an r like that. So since r hat can be expressed as r vector over r magnitude, you will sometimes see that substituted right there for the r hat. You will see, where I want it, r arrow over r. And when you make that substitution, the magnetic field law now looks like this second expression, mu0 times I over 4 pi, then in parentheses, ds cross r arrow over r cubed. So you'll see it both ways. Okay? I'll be using the first way in my work I do in this video lecture. Note then that if we apply that expression to the little element ds that you see there in the drawing, let's get the direction for dB. Remember, this is the magnetic field contribution at point P from the little element ds that's part of the conducting wire that's carrying the current I. And the direction for the dB, in some basic sense, is completely determined in this magnetic field law by the direction of that particular cross product, ds cross r hat, because that's in the numerator of our magnetic field law. And we just use the right-hand rule to get the direction of ds cross r hat. Okay? And that will give us the direction of dB at point P. So now I'm back to my original picture. The blue arrow is ds, and the red arrow is r hat. And here we are in the plane of the screen. That's where the ds and the r hat lie. So ds cross r hat must be perpendicular to the plane of the screen. So you only have two options for that direction. Perpendicular to the screen and outward towards us, or perpendicular to the screen and inward away from us. And it's the right-hand rule that tells us. So I'll go to the two-pen method. I'll use a blue pen for ds and a red pen for r hat. And I hold them as I look at them in the plane here. R hat, ds. They're about like that. I can even pick them up and look at them. And I push ds on top of r hat with the palm of my hand starting along ds, and my thumb points down. So the magnetic field contribution dB at point P from the element ds is into the screen. So we represent that with an X drawn at point P, because that's where the field is. Okay? All right. Now, that would be the contribution dB from that one little element ds. Well, to get the net magnetic field at point P, we must integrate this result that is obtained from the boxed equation over the entire current distribution. And that will give us then the net magnetic field at point P. Now, as you might imagine, that doing this calculation for a somewhat complicated wire like this one, which is winding around in the plane of the screen, wouldn't be easy. But we will limit ourselves to current distributions that have relatively simple shapes. And the first one we'll look at, so this will be an application of this magnetic field law, will be for finding the magnetic field due to a steady current in a long, straight wire. Long here is code for infinitely long. So imagine a shape like this pencil, but it goes on and on and on upward and on and on and on underneath. It's just a very long, straight wire carrying a steady current I. Okay? What's the magnetic field produced at a certain point in space, like where my fingertip is? We will use the magnetic field law to figure that out. So, got a lot of pictures here. First, look at the picture on the left. It shows kind of a side view of the long straight wire going upward and coming up from the bottom down there. It's carrying conventional current I upward, and it's steady current. Then we have picked that point P, which is some distance big R from the wire. And of course, when we say distance big R from the wire, we mean the shortest distance, the perpendicular distance from point P to the wire. Okay? All right. So, what's the formula that will give us the magnitude of B, the net magnetic field at point P from the whole wire, and what's the direction of it? Notice the point P has been chosen, perhaps arbitrarily, to be on the right side of the wire. That is something to note. All right, I'm just going to tell you the results now and talk about them with these pictures, then I'll show you the proof. Well, here's the formula coming from that magnetic field law for B magnitude at the point P. It really only depends on two things. How much current I is there, and what's that distance, big R? Because the formula is B equals mu zero, that new constant, the permeability constant, times I, over 2 times pi times that distance, big R. Okay? Note that big R downstairs is R, not R squared. Okay? And so the magnetic field gets weaker as inversely with the distance. As you get farther away, the field gets weaker. Okay? And the direction of the field at point P is into the plane of the screen. So I'll draw it like that. Okay? And in fact, it turns out that at any point to the right of this very long wire in the plane of the screen, and it goes on and on and on, the magnetic field is directed into, perpendicularly into the screen. At any point to the right of the wire, the field is perpendicularly into the screen. Now, it turns out that if we had picked the point P over here, to the left of the screen, the magnetic field law would have given us the fact that the magnetic field B is perpendicular to the plane of the screen and coming out towards us. And that is true for any point to the left of this wire, that the magnetic field is perpendicular to the plane of the screen and points outward. So we want a way to kind of try to visualize the whole magnetic field at any point produced by that long straight wire. Okay? Here's a way to do that. this picture over here at the top right. Now we're looking kind of at a top view, and so the wire is this little dot in the middle, and the current is going away from us into the screen, so they've drawn an X there where the wire is. Okay? And then they've drawn, in green, magnetic field lines produced by the current in the wire. And the key thing is that they circulate around the wire. Okay? They're more closely spaced near the wire to represent the fact that the field is stronger, and they get more farther spaced as you go farther away. And if you want to represent the actual magnetic field at any given point, like that point right there, then you draw a vector tangent to the magnetic field line at that point. So that's how they get that arrow, labeled B. That's the magnetic field right there. If you pick a different point, like right there, and want to represent the magnetic field as a vector, you still draw an arrow tangent to the magnetic field line, but it's considerably shorter now because you're farther away from the wire and the field is weaker. Okay? Okay, so you will hear people say that the magnetic field lines circulate around the wire. And notice there's a definite sense to the circulation. See these arrowheads on the circulating magnetic field lines? Okay? They are, as we look at them, circulating these magnetic field lines clockwise around the wire. Where does that come from? Well, it comes from that magnetic force law. Okay? But now we're going to show you a kind of a shortcut way for remembering the direction of the magnetic field. It's another kind of specialized right-hand rule. And it goes like this. Take your right hand, stick out your thumb, point it along the wire in the direction of the current. As we're looking at this picture, the current's going into the screen. So this is supposed to represent you pointing your thumb into the screen. And then look and see which way your fingers circulate. And as I point my thumb away from me to represent the current going away from me into the screen, my fingers curl clockwise. Right? And that's the way the magnetic field lines circulate. Then they show you kind of a side view below of the long straight wire. And the picture on the right shows the case where the current's going upward in the plane of the screen. Okay? And the picture on the left shows you the case where the current goes downward. Okay? So these are side views. And they show you this special right-hand rule. So for the case where the current's going upwards, now hold your thumb upward and look which way your fingers circulate. Right? And so they circulate with your fingertips coming out of the screen on the left side, there. And then if they could extend around, and you can kind of swivel your wrist so that they do, they'll point into the screen for points on the right side. Okay? All right. Now, the other picture shows the other situation where the current in the wire is going downward. Then you point your thumb downward, and you see which way your fingers circulate. And now they come out of the screen. Oops, let me do that in green. They come out of the screen for points to the right of the wire, and they point into the screen for points going into the wire. So we will use this kind of specialized right-hand rule as a kind of a shortcut for thinking about the direction of the magnetic field. But I want to be clear, there's no ambiguity where this direction of the field is coming from. It's coming from that magnetic field law that I showed you. And now I want to show you that and prove to you the formula for the magnetic field of a long straight wire, that one. So I am going to go through this proof. And it's up to you, whatever you feel is helpful to you, how much of this detail you pay attention to. I recommend you pay attention to all of it. okay? So that you get used to applying the Biot-Savart law. That's what it's called, the magnetic field law. Okay, but I am going to go through the proof of that result for the magnetic field of a long straight wire. So we imagine breaking up the wire into a bunch of little elements. Here's one of them, drawn with a blue arrow. And that's a little vector ds, tangent to the wire and in the direction of the current. Notice the current is denoted as traveling upward in the plane of the screen. All right, we've also just shown the distance, little r, from that element ds to the point P, where we're going to find the field, and the unit vector r hat that points away from the element along r towards P. Notice the angle theta is marked, which is merely the angle between ds, arrow, and r hat. Then there's the distance big R, which is the perpendicular distance from point P to the wire. And there's one other distance or coordinate, you could call it. It's labeled here S, and it is measured from this point on the wire that is directly across from point P to the element, ds. Okay, that turns out to be a convenient coordinate to use. All right. Now, let's write down the magnetic field law expression. The contribution dB to the magnetic field at point P from that arbitrarily chosen element ds is this new constant mu0 times I over 4 pi times ds vector cross r hat over r magnitude squared. And let's get the direction of dB first by getting the direction of that vector product, cross product, from the right-hand rule. Okay? All right, so the direction of dB at point P is perpendicular to the plane of ds and r hat, and ds and r hat are in the plane of the screen, so dB must be perpendicular to the screen. Only two options then, perpendicular and outward towards us, or perpendicular and inward away from us. And it's the right-hand rule that tells us which it is. So, two pens, blue pen for ds, red pen for r hat. I hold them as I look down at the plane of the screen. Okay? And then I do the right-hand rule with pushing blue on top of red. And my thumb points down. Down. That means at point P, I will draw a downward vector and label it dB. Note where I drew the arrow, the dB arrow, at point P, nowhere else, because that's where we're finding the field. Okay, now we know the direction for dB at point P from that little element into the screen. Now let's work on getting the magnitude of dB. That's mu0 I over 4 pi. Then I need the magnitude of that cross product, ds cross r hat, all over r squared. All right, let's just use what we know about cross products. The magnitude of ds cross r hat would be the magnitude of the first vector, I'm just going to denote it as ds, times the magnitude of the second vector. Oh, wait a minute. Magnitude of r hat. Any unit vector has magnitude 1, so times 1, times the sine of the angle between ds and r hat, which is that angle in our picture that's labeled theta. Okay? All right, so we've got the magnitude and the direction of dB from that one little element. All right, now the next thing to note is, if we think about it, the direction of the dB arrow is into the screen for every element of the wire. Not just the one that we've highlighted in blue and labeled DS, but any piece of it. You need to think about that a little bit, right? Because this wire goes on and on. What if I had looked at the piece down here? DS. Okay? Then let me draw a little dashed line towards point P, because that helps me see the direction of R hat. Now do that cross product, DS cross R hat. Your thumb still points into the screen. For any piece of this wire, you draw the DS and the R hat for that piece, and then do the right-hand rule with the cross product, and you will conclude that the DB always points into the screen. That's good news. That means it's easy to account for the direction of the net B. It's going to be into the screen at point P. So all I really have to do then to get the net magnetic field at point P is to add up all the magnitudes, the dB magnitude values for all length elements. Okay? And it is infinitely long. It is, however, also symmetric, with the kind of symmetry point being the point where S begins, the point that is perpendicularly over from point P. For every element ds that's a certain distance above that point, there's another one, much like the one I just drew, below that point, that will have the same distance r from the point and will result in the same same number for sine theta. That follows because sine of theta and the sine of 180 degrees minus theta are equal. That's interesting. And so what you can do is add up all the dBs from the top half of the wire, starting at this point right here, directly opposite to point P and going up to infinity, and then just double it. Okay? And then you will have the magnitude of B net, which I'm just going to denote like that. So that's going to be 2 times what you get when you add up all the dBs from the top half of the wire. That means starting at a S coordinate of 0 and going to an S coordinate of infinity. And that's what we're going to do. Now let me plug in this expression right here for the dB magnitude. So I have 2 times the integral of mu 0 I sine theta ds over 4 pi r squared. S goes from 0 to infinity. All right, now let's do a little bit of simplifying. Let's bring the constants out front. Things that are the same for every little element. Mu 0, I, 4, pi. That's it. Because as I move along the wire with little ds's, then the r is changing and the theta is changing. All right, so, and by the way, let me cancel the part of those, the 4 and the 2 there. So if I bring out front the constants, I have mu 0 I over 2 pi, integral from 0 to infinity, sine theta over r squared ds. We got to figure out how to deal with those symbols. All right, so if I'm going to look at that top picture there, sine theta is equal to sine of 180 minus theta. That's a basic trig identity. And 180 minus theta is this angle right there. So I can replace sine theta with the sine of that angle I marked with the double purple arc. And the sine of that angle, look at the right triangle right here. is, of course, opposite over hypotenuse, which should be big R over little r. Big R is a constant. Little r is changing as the ds moves. If I use that result in my expression for b, I have mu 0 I over 2 pi integral of, okay, sine theta becomes big R over little r, and I already have a little r squared downstairs. So now my expression looks like that. But then I need to realize, again from the picture, that little r, the distance little r, is from Pythagoras, square root of big R squared plus s squared. So with that, I can write b equals mu 0 I over 2 pi. I can bring that big R that's upstairs out front. Then I have the integral of ds over little r cubed. So that would be big R squared plus s squared to the 3 halves. And the limits would be from 0 to infinity. Okay, now that's a pretty famous integral. You can try to do it yourself as a trig substitution, or you can look up the integral in Appendix E. It turns out it's integral 19 in Appendix E. And I'm just going to write down the result then. And then we'll have to put in the limits. Mu 0 I R over 2 pi times. Okay, the result is, for that integral, s over big R squared times big R squared plus s squared all to the 1/2. And the limits for s are from 0 to infinity. Okay, note 1 factor of big R upstairs cancels 1 factor of big R downstairs. So now I have mu 0 I over 2 pi R. Now I'm putting in the limits for what is left, which is this stuff. Okay? And the limits are s values. First limit is s going to infinity. Those always have to be done carefully. But that means in the denominator, r squared plus s squared to the 1/2, as s goes to infinity, it just becomes s. Drop the r squared, and the square root of s squared is s. And s over s is 1, right? So the upper limit gives 1. Minus, then the lower limit, s equals 0. Well, there's an s in the numerator, and so I get 0, and the denominator is not 0, so 0. So the final answer for b magnitude is mu 0 I over 2 pi big R. Just like I mentioned here. Okay? Now, you don't have to rederive that. We will give you homework problems where you have to use this approach for other current distributions. But if you have an infinitely long wire, then you can just use that result. Mu 0 I over 2 pi R. Okay? All right, now I want to do one more case, and then we'll be practicing in class using this approach. All right? One more application of the magnetic field law. The magnetic field at the center of a circular arc of current. So the picture here shows an arc of wire. Okay? It's part of a circle. And of course, it's also part of a complete circuit. The wire goes on in these two directions. But we're just not worried about that, okay? We're just focusing on this part of the wire that's an arc of a circle. And in that arc, there is conventional current I flowing upward. And then C marks the center of curvature. The center of, if that were a complete circle, what would be the center of the circle? One important quantity there is the radius, which is the distance from the center of curvature to the wire. We'll denote that big R. And the other thing is the total angle phi formed from the two ends of the arc. Okay? And our task here with this application is to find the magnetic field, magnitude and direction, produced by the circular arc when we're going to pick one point only. Unlike the previous problem for the infinitely long wire, where I have an answer for the magnetic field that can be used anywhere, this answer is only going to work at the center of curvature, C. Okay? So it's somewhat limiting, but it can be helpful to know. Okay? All right. Again, it comes from the magnetic field law, and I'm going to show you where it comes from. But first, I'm just going to tell you the answer for the magnitude and the direction. Okay, first the magnitude of the magnetic field, net magnetic field, B, at that center of curvature, point C, for that whole arc. It is mu0 times I times that angle phi formed by the arc over 4 pi big R. Okay? Warning with using that result. The angle phi must be in the dimensionless SI unit of angle, which is the radian. Radian, not degrees. Now, the magnetic field law, specifically ds cross r hat, will give you the direction of the magnetic field. But there is a kind of a specialized right-hand rule shortcut that you can use. And it's very similar to what we did for the long straight wire. For the long straight wire, we just stuck out our thumb in the direction of the current and see which way our fingertips circulated around our thumb, given the direction of the current is being up or down. Similarly here, curl your thumb away the current's going in the arc, and then look which way your fingertips circulate. So our current's going upwards around the arc, so I put my thumb upwards, and I see that to the left of the wire, my fingertips point up towards me. So that means the magnetic field is coming out of the screen towards me at that center of curvature point. Okay? All right, so how do we get that result from the magnetic field law? So we start with the expression of the magnetic field law. dB arrow equals mu0 over 4 pi times ds arrow cross r hat over r squared. Okay, all right, now here's a picture on the left, kind of blown up, and the ds is really drawn too big because it's really just a little segment, a little infinitesimal segment of the wire, and we make it now into a vector, ds, that is tangent to the wire and in the direction of the current. Remember, the current's flowing around this way, okay? Then draw, so that, notice that's tangent to the wire, okay? Then draw the distance from that element to the center of curvature. That's little r, and that'll help you draw r hat, because that points along little r from the element towards the center of curvature. All right. Now let's use the right-hand rule and ds cross r hat to get the direction of dB. So we just do the right-hand rule. ds and r hat are in the plane of the screen, so dB must be perpendicular to the plane of the screen. That gives me two possibilities, perpendicular and upward or perpendicular and downward. And I do the two-pen method with the blue pen for ds and the red pen for r hat. And I push ds on top of r hat, and my thumb points towards me. So that means the dB at point C is coming out of the screen towards us. So draw the dot encircled over at point C. Don't draw it anywhere else, but at point C. That's where we're finding the field. That's going to be true, by the way, for every little ds in the arc, that the dB at point C will be coming out of the screen. So now we just focus on the magnitude of dB. So that's mu0 I over 4 pi, magnitude of ds cross r hat over r squared. And use what I know about cross products. Magnitude of ds cross r hat would be the magnitude of ds times the magnitude of r hat, 1, times the sine of the angle between ds and r hat. But look at the picture. Look at that little right angle symbol. ds is tangent to the circle, r hat's along the radius. That's a 90-degree angle, isn't it? So I'm just taking the sine of 90 degrees, which we know is positive 1. And all of this is over r squared. So this simplifies to mu 0 I ds over r squared. So now all I do is add up all the dBs to get the net B at point C. So that's the integral of mu 0 I ds over r squared. Now let me talk just a little bit more about that ds. There's a blown up region of the wire. And the ds is a little arc length along the wire. Here's the center of curvature of the arc. Let me extend out radial lines to the top and bottom of that ds. The distance here is r. Let me call this little angle right here d phi. Then from basic geometry, I know that ds is equal to r d phi. And now I'm going to substitute that for the ds in the B formula. I'm going to bring the mu 0 I out front. Then I have r d phi over r squared. Cancel one factor of r. Every ds is the same distance, little r, from the center, right? Because the center of curvature is a special point. So I can bring the little r out front in this particular case. And so then the formula for the integral is just to add up all the little angles, d phi, from one end of the arc to the other. But that'll just be the total angle phi formed by the arc. And, I beg your pardon, I dropped the 4 pi. I certainly didn't mean to do that. Certainly can't do that. And I have the formula that was provided. Mu 0 I phi over 4 pi r, where the phi has to be in radians. And if the current's going upward and along the arc, then the B is out of the screen. Okay, so I just leave you with some class engagement practice with circular arcs of current. And the practice goes like this. We have 3 circuits. They consist of concentric circular arcs, which are either half or quarter circles. And these arcs have either a radius r, 2r, or 3r. So smallest, middle, and biggest. Okay? The circuits all carry the same current. And let's just say, for the sake of specificity, that in each case, the current I flows around in the sense that you see here, which would basically be counterclockwise. Same I. Okay? Our task is to rank the 3 circuits according to the magnitude of the magnetic field produced at the center of curvature, where the dot is, greatest to smallest. So what I recommend you do is, using the formula right up above, you can just see it there, for the magnetic field at the center of curvature of an arc, and careful use of the right-hand rule for the direction of B, get a symbolic expression for the B at the dot for each of those cases. Okay? It takes a little bit of work, but it's good practice using that formula right up above. Now, some of you, I bet, are wondering about the effects of these regions right here and here, here, and here, here, and here, which are not arcs at all. They're straight segments. Okay? There's some good physics in thinking about those pieces of the circuits, because I'm contending that you only have to worry about the circular arcs and their contribution to the magnetic field at the dot. And the reason, so that means what I'm saying is you don't have to worry about the straight segments. They make no contribution to the magnetic field where the dots are. Do you see why they don't? It has to do with how they line up relative to the dot. And that magnetic force law, specifically the ds cross r hat part. Let you think about that a little bit. Okay? All right, so rank the net magnetic field at the place where the dot is for those three circuits. Okay? And then we will be talking about this magnetic field law in class. And that's all for this video.